Welcome to my presentation about the Zen, a complex campaign of harmful Android apps. If you consider all the talks about malware that you have seen, there's probably a large percentage that deals with a specific malware family, not necessarily a set of apps that are coming from the same author. This is slightly different. And what started this investigation is I found an app which had an unusual property. This property will be mentioned later on, but this app led me to find a whole portfolio of apps that were developed by the same author, and this talk will guide you through that portfolio. We believe that that these apps were written by the same author or the same group of authors, and it contains repackaged apps with a custom advertisement SDK. It contains click fraud apps that root your phone in order to create fake Google accounts, and apps that are obfuscated and modify the system in some way. Okay, let's start. So first one, as I mentioned, is the custom ad SDK. And what is a custom advertisement SDK? This is, you can think of it like a proxy server for the apps. So for the ads. So what it starts with is you have an app with an ad SDK, and this ad SDK is requesting an ad from the command and control server, and the command and control server gets the ad link from the real advertising network. It downloads the ad, and then it returns the link to the downloaded source, to the downloaded resource. That way you have a proxy to all the real advertising networks. And when you have a proxy to all the real advertising networks, what you end up with is you end up hiding them from the actual app. So when you are reverse engineering an app and trying to find out which advertising network it's using due to this proxy infrastructure, that won't be possible. And it also can be used to hide the ad network abuse. So when you're reverse engineering the app and it's doing some kind of an ad fraud, what happens is you don't really know which ad network is being abused by this app because it's hidden behind the proxy itself. This is a fairly easy concept, and the apps that use this SDK can be divided into two groups. So first one is what you can see in the screenshot here. It's the actual game that's on top, and when you click on play, you will go to the game and have the same experience as you would if you were playing a game. And what you see below the play button are ads. And these ads are coming from the ad SDK. You can see that the user is maybe inclined to click on the ads instead of clicking on the play button. And when that happens, the ads are from the CNC. But when the user clicks on the play button, they will get the same experience because, again, the app is repackaged. It's the same popular app that the user wanted to use, just in a different form with additional ads. And the other kind of apps that use this as ad SDK is it's not real apps, but apps based on the real app, and they mimic the popular apps, but they do not provide the same functionality for the user. So they only pretend to be the app that user wants, but instead they will just show ads to you. And that may not be a great user experience, obviously, because user only gets to see the ads that are coming from the CNC. So this is fairly simple. And as I said, this custom advertisement proxy SDK is not malicious in itself, and those proxies don't necessarily have to be malicious, but they allow the attacker to hide the real ad network. So this is one of the simplest apps in this malware author portfolio. Now we can move on to slightly more complex apps that are doing some kind of ad fraud, and this is click fraud. So click fraud in general is defined as just clicking on an ad or generating an ad click instead of the user clicking on the ad, it's something else that's clicking on the ad automatically. This can be done on Android in 3 different ways. This can be done purely in JavaScript. So you load a website and that website contains a JavaScript, and that JavaScript clicks on an ad automatically. It's nothing related to Android. It just happens that the website that's loaded is clicking on the ads. It can also be done using Android API to simulate the user click. And when the user click is simulated, the ad is clicked, and it's slightly harder for the ad network to detect because the JavaScript part is obviously loaded through a website, so it's a part of the website, but here the ad network thinks it's coming from the Android API. It can also be a mix of both, and it's a mix of both when the app is exposing a JavaScript interface. JavaScript interface is a way for a website to use JavaScript to call a Java method that's implemented in the app itself. So the app exposes a JavaScript interface. The JavaScript code calls a method that's exposed using the JavaScript interface, and then a Java code is executed on the Android. And that Java code can, for example, simulate a click on an ad. And that way the attacker gets some information from the website, and based on that information, they can click on an ad. And you can see that apps that are click fraud are blocked by Play Protect. So what you can see in the screenshot is when the app that was a click fraud app got blocked by Play Protect. And you can also see that there's a short explanation of the type of malware that was blocked. So it says this app can simulate a tap on your screen's content, such as an ad in the background, right? So during the install process, when you see that that warning, you will get some information about the app, and you can interrupt the installation process and not install the app. The way this click fraud was done in this particular set of apps that come from the same author is through a rather large JSON object. So the app contacts the CNC server, it gets back a JSON object with a rather large list of different key value pairs. And the list contains the strings that will be matched against the HTML of the website. So you can see in the screenshot here is you can see the keyword, and the keyword is something that will be matched against the HTML. And then you can see the JS key, and JS is the JavaScript snippet that will be executed whenever a keyword is found on the HTML website. So the goal of the app is to look through the website and then execute JavaScript if something happens. And you can see the first example here. It looks for an A element that is of a class show height btn next. And that keyword, if it's found, then a JavaScript will be executed, and that JavaScript looks basically for the same element and then clicks on it. That way the app can ensure that the keyword was found and that the element is on the website, and it can execute the JavaScript and not worry about the element not being found because it's obviously there. When I said that there is a rather large list, I also mentioned at the beginning of the talk that I found an app that had a really weird property, and that weird property was the CNC response, and the CNC response was unusually large, which in some cases may mean that the app is downloading an additional code from the server or an additional app from the server and is doing something with it. But in this case, the thing that it downloaded from the CNC was this list, and this list was quite large. So what you can see here in the screenshot on the right hand side is that list. It's actually 1/3 of that list, and you probably cannot see the characters because they are so small, but it's still 1/3 of the list. So if I copied it 3 times, it would take the whole slide and you couldn't see anything. And that's 287 kilobytes of click-through commands. So that's 287,000 characters of click-through commands that are being transported from the CNC or received from the CNC. And this means that the author doesn't necessarily care about accuracy or compactness, but it works. It just needs a bit more of the processing time to go through the whole list and find the elements that match and then click on it. So, as I mentioned, applications that perform click fraud are classified as malicious applications, and you will see the Google Play Protect warning if the app is classified as a potentially harmful application, and then your install process will be interrupted, or you will be asked to uninstall the app from your phone. Okay, let's move up the technical complexity of the apps. So I mentioned the very simple ad SDK network, and then I mentioned the click fraud. Now we are going to routing and account creation. So the way this app routes the phone is it uses an API to connect to a server and then download something they call solution. Solution in this case is an exploit that is downloaded from the CNC. And the app sends the device info to the CNC, and then CNC decides which solutions or exploits will be downloaded and will work on this particular device. So what happens here is that the exploits that are on the CNC are protected in a way from the reverse engineers, because you have to know which device you want to exploit, and then you send that information to the CNC and it chooses the exploit for you. So you never know which exploits are available on the CNC and which devices can be targeted. Once you get this solution, there is a call to set crack type. This is just a way to define the interface between the solution and the app. So there is some common interface between them so that the app knows how to call the exploit or the solution. And it gets the file name, and if it's successful, then it will upload the information that is successful back to the CNC. So when the exploit works, it has the root privilege. And then what it does with the root privilege is it enables accessibility services. So accessibility services are these services on Android that allow, for example, people that have their eyesight impaired to be able to use the phone in a more accessible way using, for example, a screen reader. So obviously the app that has accessibility services has some a bit more privileged access to the device. For example, it can read the screen in order to read the screen. So this app, if it successfully rooted the phone, it already has the same privileges, but it uses accessibility services to have some kind of an API. So it doesn't necessarily elevate the privilege because it already has the root account. And you can see that first thing it does, it gets the list of enabled accessibility services, then it adds its own accessibility service and saves it as enabled accessibility services, and then sets accessibility enabled to 1. So what this does is it just adds an element to the list for the user. So user is not aware of that. If the user was aware of that and it went through the regular process of enabling the accessibility service, user would see something like this. And this is actually from the app itself, from that app that requests the accessibility services after rooting your phone. But the user, again, won't see it because the app does it for them. You can see that the screenshot here asks for a privilege to observe user actions and retrieve window content. So again, it will be able to read the screen and observe some actions. Okay, what the accessibility is used for is it's used to create fake Google accounts using the account creation wizard. So these are some screenshots from the account creation wizard. You can see that there's an entry verification code, basic information about your birthday and gender, and how you'll sign into your account, so your username. And you can see the code of the app below, and that's the title contains enter the code. Or the title contains basic information or something like that. And based on the title of the screen, different action will be performed. One of the titles that you can see is base64 encoded. And this is the only base64 encoded or the only obfuscated string I saw in the whole app. I don't know why the author chose to obfuscate that. It also correlates with the fact that there is an apostrophe in the name. Maybe that's related, or maybe they were trying to circumvent some kind of an NAV fingerprinting or something like that. But this is the only string that's obfuscated, even if it's just base64. So now it has access to this account creation wizard, but it needs more information in order to create the account. And this information is supplied by the CNC. So first thing is the phone number, and the phone number is sent from the CNC. So the app contacts the CNC, gets the phone number, but also in order to verify the phone number, it has to get the one-time password. The one-time password is sent using a text message. So the app needs to contact the CNC again to see the text message. And this is what you can see is being done here. First, it got the phone number, and then it contacts the CNC with that phone number that it used for verification and says, hey, did you see any text messages coming to that phone number? And if the CNC saw some text messages, it responds with the text message content, and this text message content is processed here. As you can see, the response starts with MSG ampersand, and then it looks for is your Google. So it looks for the verification code, it parses the verification code and gives it back to the account creation wizard. As I mentioned, it all started with routing. So the first step is to find a solution, what they call, or an exploit. And it's very hard to find a reliable exploit for newer Android devices that works across all of the Android devices. So the risk of getting infected is slightly or significantly lowered on newer Android devices. Now, let's move to code injection and obfuscation. This is a even more technically complex part of the app, and this is something that app can do because the app was able to root the phone. So when you have root, you will have the ability to ptrace into other apps. And this is the diagram for the code injection. So it starts with the source application, which is on top in light gray, and the target application is below in the dark gray. The source application, the way we will read this diagram is from the left-hand corner, top corner, and then we will move down in the diagram. So you have the source process. It calls the inject remote process method from the LMT inject framework. And the parameters to that method are the target process ID, the one that we want to inject the code to, the name of the file where we can find the code that will be injected, and the method that we will inject to the target process. So what you can see here is that it ptraces into the target process. It can do that because it's rooted. The phone is rooted and it has the root privilege. And then it will move the program counter to some other place. And in order to do that, it has to map memory in the target process, just so that it can put the shellcode that would load the inject.so file, and it will start the do stuff method. So in order to do that, it has to find libc. The way it finds libc is by going to /proc/process_id/maps of the target process. And that is where it will find the mapping of libc in the target process. And then it can use offsets from its own mapping of libc to find where mmap function is. And it can allocate the memory in the target process. And in the allocated memory, it will just have the code to dl open inject.so file and then call the method, or find the method and call it. And again, dlopen and dlsim are found the same way that mmap is, by looking at the mapping of libc and then looking for the specific offset. So this is how it can execute code and do stuff in inject.so. But this whole complex process of injecting the code into the target application is used for a very specific purpose in this case. And this specific purpose is to get the CAPTCHA image. So during the whole account creation process, it may happen that the user will be asked to solve CAPTCHA. And the way it's handled by this particular malware is it extracts the CAPTCHA image. For that, it has to inject code into the account creation wizard. And it will extract the image, send it to the server, and then the server will respond with the CAPTCHA solution. I don't know whether it's done automatically or manually, or in what way the server solves the CAPTCHA, but it just sends the whole image and gets the code back. So what you can see here is basically it. It gets the CAPTCHA image view element, UI element. This contains the CAPTCHA image, and then it requests the code that this decrypted to. So it encodes the image using base 64, sends it in a JSON object, gets the response with code, enters the code into the account creation process or account creation wizard. It also uses that code to hook internal methods. And the way this is done is by looking at the methods that may interrupt the account creation process. So for example, one of such methods would be reboot. If the phone is requested to reboot, for example, by the user, this may interrupt the account creation process. So what this malware does, it creates a hook in the Power Manager service reboot method. And that hook doesn't do anything apart from returning 0. So it effectively stops the reboot. And you can see here something called dexposed is used, is used, and it can only be used because the phone is rooted, right? So then it finds the find and hook method for reboot in the Power Manager service. So you can see that there is a method called before hooked method. This will be executed before the reboot is called. And as I said, the only thing it does is returns the value, effectively stopping the reboot because the value is already returned. So the method doesn't have to run, and the phone doesn't have to be rebooted. It also hooks a bit more. So it also hooks a method that is used to process some keys. You can see that key power, menu search, volume up and volume down, and volume mute are being hooked. And instead of processing the event of the key being pressed, it will just return the value 0. So even if you click on the power button, you probably won't see the reboot option. And if you want to reboot your phone, it's also hooked. So you won't be able to reboot your phone. So I said that code injection was possible because the phone is rooted, but again, you have to gain root, disable SLNX, and on newer Android versions, the /proc file system is more locked down. So you cannot look into maps to find out where the libc is because you cannot access the proc file system for a different process ID and find the location of libc. So this framework will fail on the newer Android versions. And the DES is used here to obfuscate the sample. So this is pretty interesting. The app contains an asset file, and that asset file is in the X directory, and its name is a number. And this number in the file name is used as a string, as a key to the DS. It's not used as a number key, but it's used as a string key, and then it's decrypted, and the code is loaded and the code is executed. So some of the versions implement this kind of obfuscation. So we know how the code is obfuscated, what it does, how it creates the account, how it deals with the captcha images, and all of that. So let's move on to the persistence. And persistence is just a way for the system to create to hold on to the whole Android system. So it's a way for the malware to persist. The first method is it writes to installRecovery.sh. InstallRecovery.sh is this script that is called during the boot process by initd. And this installRecovery.sh contains lines of script. And one of the lines that is added by the malware is just command to execute the daemon, the ZLT daemon, which makes sure that the app is running. So the app will run during the boot process. Another way of achieving persistence is by installing apps in /system. So installing the apps in /system allows the app to make it a bit harder for the user to disable it. If app is installed in /system, the user can disable the app, but the file will stay on the system partition. And this is due to the way that verified boot works. The verified boot feature calculates hashes from the system partition, and these hashes have to be the same as the hashes that were either during the update or in the factory when the system image was created. So that makes sure that the system partition was tempered, and if the app from the system partition was deleted, then the hash would obviously be different. So that's why the apps on the system partition are not deleted, they are disabled. And what this app does, it remounts the system partition as read-write, because the system partition is read-only, and then copies itself to the priv app directory where some of the pre-installed apps live. And once it's copied there, it's viewed as a system app, so it can still be disabled, but it cannot be as easily removed from the system. But the only difference between disabled and removed is that the file is there, but the app is still not running. Third method of persistent is by adding code to the activity class. And now the activity class is one of the classes in the Android framework, so it's not so easy to modify. The way this malware modifies it checks whether the build fingerprint is the one it wants and one it knows about. And then it swaps the whole framework.jar file. This is a slightly dangerous operation, because if you don't have the right framework.jar file for the right device, what will happen is the device can be effectively bricked in a way. So the malware has to first check whether it is on a correct device, and then it can swap the framework.jar. And the only thing it does is it connects back to the server saying that I'm still here. So it just sends back a ping. And the activity class itself is a UI element on Android. So to put things very simply, anytime you interact with the UI, it can be an activity class. So if you open a new app, you open a new activity, this statistics method will be called if your phone is infected with this particular malware, and it will connect back to the server. And finally, the fourth method is by injecting into the system server process. So the system server process is something that just runs in the background constantly in Android. And because it runs in the background constantly in Android, it will persist until the reboot. So if you inject code into there, your code will run until the reboot. So the malware injects the code using basically the same framework that I described. And then it also checks whether the tracer PID is there. And the tracer PID is the process ID of the app that did the ptrace. So you saw in the previous slides that there is a source app that ptraces into the target app. And when it does that, the tracer process ID will be altered or will appear in the proc file system. So the app can check whether the injection was successful by looking at the system server tracer process ID. And if it's there, it doesn't have to inject the code again, and it can report back that the injection was successful. So I mentioned 4 methods. This is a small summary. 3 of them are protected by verified boot. So I said about installing the app in the /system directory. Same applies to install recovery. Install recovery is also part of the system image. So if it's altered by adding additional line of shell script, it will be detected by verified boot, and the boot process will be stopped because the system partition is different. Swapping the framework jar, same story. Android framework is part of the system partition, so verified boot will detect any changes to framework.jar. And when you inject code into the system server process, you're injecting code into memory. So obviously verified boot doesn't play a role here, but it won't survive the reboot. So all 4 combined don't really provide a good persistence against new Android versions. And one other thing I want to mention is the actual timeline of the apps. So the way I presented the apps here is by starting with a very simple app that had ad SDK, additional ads in the repackaged apps, or pretended to be other apps but with ads in it. Then we went to click fraud, then we went to routing, then we went to account creation, code injection, and all that technically complex stuff. So I kind of lied to you, and the way I lied to you is I presented them in the order of increasing technical difficulty, but this is not the same order as the timeline. The apps were created in a different order, and this order supports what we saw, and that is that the malware developers are moving away from routing exploits, because routing exploits are harder to find. So the first sample that we saw was using dynamic code loading. So it was very hard to definitely say what it was doing. It was definitely displaying ads, but it also downloaded additional code from the CNC. So it's possible that it was doing more than that. Then we saw the routing exploits. It was less advanced than what we saw here. Obviously, it developed over time, but it tried to get root privileges. Then we saw the click fraud. So you can imagine that after the unsuccessful routing attempts, the author moved on to click fraud with the enormous JSON that attempted to click on ads. And then they introduced the DES obfuscation that I was talking about with the asset file. So the timeline is slightly different than what I presented here, but I think that presenting it in a order of technical difficulty provides a more useful presentation. So, as I mentioned, the author had to pivot from routing Trojans because it's harder to exploit an Android device. So they moved on to something different, like click fraud, even though it's slightly less advanced than the routing Trojan. Okay, so let's sum up what I was talking about here. First, The verified boot makes sure that the system partition is not altered, which prevents the persistence part. Rooting is harder, more expensive. Sometimes it's not even possible, which prevents the app from rooting the device, which prevents it from enabling the accessibility and creating fake Google accounts. Code injection open source frameworks like the one I described here are broken since Android Nougat because proc is more locked down, so you cannot so easily go to maps and by going to maps see where the libc lives, and you cannot so easily navigate the memory of the other process. We are also actively looking to better detect click fraud apps. I showed you the screenshot that will be shown to some users if the app is deemed to be a click fraud. We are also looking at root enabling app droppers. So again, something that roots the phone and then drops the additional apps and makes them slightly more persistent or something like that. We are looking into it and making sure that it won't happen anymore, even though the exploits aren't so widely available. So, summary of the whole presentation is that I wanted to present something slightly different than what you will usually see. So instead of focusing on one malware family, I presented you a portfolio of different malware families that are linked by the same author or the group of authors. Android malware families usually tell only one side of the story. And that means that eradicating one malware family just may mean that the author will move to a different malware family. It doesn't necessarily mean that the author doesn't come back with something else. So we have to take a step back and not only figure out what the malware family is doing, but maybe what the author goals are, what the author may do in the future in order to create more malware and monetize the infections in a more profitable way if one avenue of achieving that profit is closed. Okay, and obviously attribution requires different tools. So not only we have to take a step back, but we also have to change our mindset in order to make sure that we do attribution correctly. That is all. Thank you. I will be available on the Discord channel where you can ask questions. If you don't manage to ask questions on the Discord channel, you can also ask me on my Twitter account. And thank you again. That is all.